right, good morning, afternoon, night, or whatever it happens to be for you at the moment. Welcome back. Our next section out of chapter 3, section 5 is going to be complex numbers. It'll be the second to last one that we cover before our next exam, which will be on this chapter. But anyway, what I'd recommend, take a minute, pause, jot down the information I have here on this first board, and I'll talk through it briefly here. So think about equations that we have solved in the past. We've always talked about what are called real numbers. It's what you've known since you were in the womb, or at least since you were in kindergarten anyway. Real numbers can involve fractions, decimals, positive, negative numbers, pi, e, any number of things that you've seen in the past. Complex numbers now involve what are called imaginary numbers. So I'm sure you're very excited to know that there's a whole new number system that you've never worked with yet that we're going to start with now. The whole basis for complex numbers all deals with being able to take the square roots of negative numbers. So in the past, if you would have been given an equation that looked like this, x squared equals negative 4, say, you'd have said that there's no real answer, no real solution, no solution, because we've always said that the square root of a negative number is undefined. However, with complex numbers, these now give us the ability to take the square roots of negatives and solve any quadratic equation. Define the imaginary number I squared as equaling negative 1, and we're going to see why that's important here in just a few minutes. So I squared equaling negative 1 is going to be what we define as an imaginary number. Moving over to this equation now, I can now solve this instead of just saying it's no solution. Okay, and I'm going to write down just so I have it side by side here, keeping this in the back of our mind. I squared is negative 1. Solve it like I would any other equation in this form. I take the square root of both sides. I'm left with x equals, and I have to remember plus or minus. And now how am I going to work with this square root of negative 4? Well, there's going to be a 2 involved, as you could probably predict, because the square root of 4 is 2. Here's what I do. I break up this as the square root of positive 4 and the square root of negative 1, because 4 times negative 1 is negative 4. So the square root of 4, of course, is 2, as I alluded to. But what is this square root of negative 1? This is where the imaginary number comes into play. And it all bases around this. If I squared is negative 1, think of taking the square root of both sides of this equation. I would be left with I is equal to the square root of negative 1. Therefore, square root of negative 1 is defined as I. So again, the square root of negative 4, or any negative, is going to involve what is called, or what we define as being an imaginary number. Okay. So complex numbers involve these now imaginary numbers of square roots. We talk about standard form with any number of things that we do in mathematics. And there is also a standard form in which we format complex numbers. A plus bi is what the general form or standard form looks like. So again, complex numbers and imaginary are not exactly the same thing. Imaginary numbers are involved in complex numbers, but a complex number is a combination of a real number component, so maybe just a number 6, whatever, a real number, added or subtracted to an imaginary component. So when I am working with complex numbers, this is just the format. I always see the real number first, added to the imaginary number second. So again, little minor things that you always have to keep in mind. We do operations with complex numbers, okay? Just like I would with real numbers. And the whole basis, a lot of what you're going to see here, boils down to things we already do, such as combining like terms, working with exponent rules. The first operation we're going to see is a combination of addition and subtraction. And we'll say simplify. Now the big hint I'm going to give here with anything involving addition or subtraction is I just want to think of this like combining like terms. Just like I can't combine a constant with a variable, I can't combine a real number with an imaginary number. Okay? So first one we'll do here, pretty simple one. 4i plus 6i plus 2 minus 7 minus I. All right, so treat this just like a string of like term combination. I could combine anything that has an imaginary number and anything that is a real number. So I can add 4i and 6i to be 10i. 10i minus I would be 9i. Next, I see two real numbers. 2 minus 7 is negative 5. Now, see if you can catch my mistake here. This is going to lose you a point on a quiz or an exam. All goes back to standard form. So to be fully simplified and formatted, real number first, negative 5, imaginary number second, plus 9i. So again, that's it. It all boils down to very familiar concepts. Number 2, we'll do another quick one involving adding and subtracting. 5 times the quantity 6 minus 2i minus 4 minus 6i. Okay, so this one, there's a little distributing first, but that works exactly like we would normally with variables and coefficients. 5 times 6 is 30. 5 times negative 2i is negative 10i. Second part, I just have to distribute a negative into both. I get negative 4. Negative of negative 6i would be plus 6i. So finally, just like we did before, we combine the real numbers with real numbers, imaginary with imaginary. So the real number first, 30 minus 4 is 26. Negative 10 plus 6i would be negative 4i. There we go. Adding and subtracting with complex numbers. Multiplication. Now, what I would like you to do here, make sure you jot down this quick 4-part chart. Okay, so a powers of I chart that repeats in cycles of 4, actually. So, we're going to see where this comes into play in just a second. But a big idea here is that in a final answer, it is not fully simplified unless I see at most powers of 1 on my imaginary components. If not, it could be rewritten as something else. Okay? So, I squared we've already talked about is negative 1. The easiest jump to think is if I go from I squared to I to the third. What did I do? I multiplied by an extra power of I. Well, think about what I would get if I multiply negative 1 by I. I just get negative 1i. Think of it then if I multiplied to go from I squared to I to the fourth. I squared times itself, I squared, is I to the fourth. Therefore, negative 1 times itself, negative 1 times negative 1 is positive 1. And this cycle repeats. So I to the fifth would be the same as I to the first. I to the sixth, same as I squared, so on and so forth. So again, bottom line, not to digress too much, but all powers higher than 1 must be reduced to something from here. First one. So multiplication of complex numbers. Now, just like before, I'm going to multiply real coefficients with each other, and I'm going to multiply imaginary numbers with themselves. And what that's going to boil down to is exponent properties. So this one, careful, this is not addition. I'm not doing negative 1 plus 3i to get 2. This is multiplication. This is just going to be negative 1 times 3, which is negative 3. Now think exponent rules. If I told you what's x times x, hopefully immediately you can tell me it's x squared. So therefore, I times I is simply I squared. Now remember what I just said though. Any power higher than 1 must be rewritten. This is going to be the most common one here. Anywhere I see I squared, the way it is defined, I can replace that with negative 1. So this very simply boils down to just negative 3 times negative 1, which is positive 3. It's as simple as that. So exponent property rules. And the last one of multiplication, number 2 here. Just kidding, 2 more. 4i times 1 minus I. This one, it's a simple distribute step. Real number times real number, 4 times 1 is 4, and I tack on the I. 4i times negative I is negative 4. Careful with this, I squared. Which once again, just like the last problem, this I squared must be replaced with negative 1. Now I just multiply negative 4 and negative 1 to give me plus 4. Once again, I'm not quite there yet, just have to reverse it to get standard form of a complex number. Okay. That'd be it. The last bit of multiplication that we'll see, once again, involves a very familiar concept, hopefully. Number 3, 2 minus I times 6 plus 2i. So hopefully a strategy right now and a technique jumps right out at you. This one we're going to use either the FOIL or the double distributing technique, however you like to remember it. All right, so I just go 4 multiplications. 2 times 6 is 12. 2 times 2i is plus 4i. Negative I times 6 is minus 6i. Negative I times 2i is negative 2i squared. So once again, I see a couple like terms as we usually do when we FOIL. 4i minus 6i is negative 2i. Here we go, the rewrite step again. That's going to become negative 2 times negative 1. Negative 2 times negative 1 is positive 2. And finally, we just have 2 real numbers to add at the end, 14 minus 2i. So again, this imaginary value we work with almost exactly like it's a variable. Okay, so the final bit that I guess the biggest use of complex numbers is that we now use them in solving equations. Very similar to what I showed at the very beginning of the notes with that x squared equals negative 4 equation. With complex numbers, all quadratic equations now have solutions. So in a problem where we before might have said no real solution, well, that's still true, but we may get too complex or imaginary solutions now. Think about how we could solve any quadratic equation. We think factoring, but we also many times, and this will be what's going to be used here a little bit in this section, the quadratic formula. So you didn't know I was American Idol worthy. I'm not sure if anyone's a Notre Dame fan. I certainly am not, but here's a nice little song for you to remember, set to their fight song. X equals negative b plus or minus the square root of b squared minus 4ac all over 2a. And there you go, I'll be here for another 3 weeks or so. But anyway, that will be used for our equation solving if we can't factor. Remember, this is always a viable option. Okay, so solve, but now instead of saying no real solutions, if we get them, we now have complex numbers to work with. 0 is equal to 3x squared minus 2x plus 5. Okay, so this one, I'll save you a step of thought. It's not factorable. So that means I'm instantly going to think quadratic formula to solve this equation. So those are my A, B, and C coefficients. I fill into the formula. X is equal to, so negative of B would be positive 2 plus or minus the square root of B squared minus 4 times A times C all divided by 2 times A. So again, there's filling the coefficients into the formula. First thing I like to do, evaluate and get one number underneath the radical first. Negative 2 squared is 4, always careful. Negative squared is positive. Negative 4 times 3 times 5 is negative 60. On the bottom we can get a value there, 2 times 3 will be 6. So in the radical now, 4 minus 60 will get negative 56. So if I were to ask you right now, what types of solutions are we get? We're always going to get 2 now. Are they 2 real, or are they 2 complex? And the answer is that they're complex solutions because we are trying to take the square root of a negative number. What I like to do when I do these problems is off to the side break down this radical. So I have to do simplest radical form here with negative 56, and I'm just going to replace it with my simplified work. As we did at the beginning of class, break down 56 into the square root of negative 1 times positive 56. As we've seen, the square root of negative 1 and defined it, that's just I. 56 can be rewritten as 2 radical 14. Okay, so again, simplest radical form, a concept I'm hoping you're very familiar with at this point. And again, I would just reverse this. I wouldn't see like x times 2. I would always write it as 2x. So 2i radical 14, I'm going to replace a radical negative 56. So instead of radical negative 56, this is now 2i radical 14 over 6. The last small thing I can do to simplify, I like to think of it as, is there a number that is common in that triangle of numbers that I can divide from all 3? The answer is yes. They're all even, so I can divide each by a 2. 2 divided by 2 is 1. 2i divided by 2 is just 1i, so I radical 14. Do not try to divide the 14 by 2. Numbers in radicals cannot be divided by numbers outside of radicals. Divided by, on the bottom, 6 divided by 2 is 3. So again, final answer, they're imaginary solutions or complex, but now we can solve any quadratic equation. So 1 plus or minus I radical 14 over 3 would be the solutions there. Final example. So one more equation. X to the 4th, or 0 equals x to the 4th plus 8x squared minus 9. All right, now this one hopefully you notice is not a quadratic equation. Hopefully you know the reason for that. This one has a degree that is higher than 2. It's actually 4. So I'm going to expect a maximum of a total of 4 solutions. Now, I may get a combination of real, imaginary, I may get some, all of one, but we'll see. So I can't really use the quadratic formula because again, it's not a quadratic equation. However, I'm going to think of this as being quadratic-like. So pretend that this were an x squared, an 8x, and a minus 9. Or even write that off, on your notes there on a scrap piece of paper. Hopefully you notice that equation is very easily factorable. I can treat this exactly the same way, just adjusting a little bit. So again, pretend I gave you the x squared plus 8x problem. This would factor as x plus 9 times x minus 1. So factors of 9 that subtract 8, positive 9, negative 1. Here's all I have to do to account for that power of 4. If x times x is x squared times x squared gets me x to the 4th. So that's all I have to do there. Now, what I have to also do, though, is check to make sure I can't factor further, and I can in this one. X squared plus 9, this is unfactorable. It is not a difference of squares. That's where we're going to get 2 imaginary solutions, actually. So that's going to stay for now, but we'll show how to deal with that in a second. This one I can factor. This is a difference of squares. This is just x plus 1 times x minus 1. So I get 2 solutions right away that are real numbers. I get x equals positive and negative 1. I expect 4 solutions, however. The other 2 are going to be imaginary. Here's all I do to solve this equation. It's going to look very similar to the one that I began class with in this video. Take x squared plus 9, set it equal to 0, subtract 9 from both sides, and now look what we're left with. We're taking the square root of a negative number, which is an imaginary number. Just remember plus or minus, square root of 9 is 3, square root of negative 1 is I. So there we go. 4 solutions, 2 complex, 2 imaginary. So in conclusion there, we got 4 solutions total, 2 real, maybe I misspoke, I forget what I said. two real solutions, two imaginary solutions. And again, the reason we get that, degree of 4 at the beginning. So again, big idea here, square root of -1 is now a value that we can actually work with. It's what's called an imaginary number, used in equation solving. We can do operations with them, as you saw, just like we can real numbers. So again, ties up the second to last section of chapter 3. This will be the last section that'll be on your next quiz, which will be this week, covering sections 3, 4, and 5. So again, email me as always if you have any questions, and have a great day.